Okay, welcome. So this is going to be a relatively short video here. We will pick up more on this tomorrow, but I want to give you a short introduction to section 9.6, which is called molecular orbitals. And the symbol for molecular orbitals are MOs. We call them MOs. Okay. So yesterday we spoke about hybridization, which is an extension of what's called valence bond theory. The idea that atomic orbitals overlap with each other. And so, for example, if you have a 1s orbital and another 1s orbital, they overlap with each other. And the greater the overlap, the better the bond is. The stronger the bond is, the shorter the bond is, right? So that's overlapping atomic orbitals. And then we said, in order to maximize overlap, sometimes the central atom will mix its atomic orbitals. It'll take the 2s orbital, mix it with one of the 2p orbitals. They're at the same level, right? Second shell. And when that happens, you get these two new orbitals, which are called hybrid orbitals. And those are more directional. They point towards the surrounding atoms better. And therefore you get stronger bonds, you get more overlap, right? So that's one theory of bonding, but there are other theories of bonding that chemists use. And in fact, really probably what happens is these quantum mechanical waves are behaving in whatever ways that they are in order to make the bonds as strong as possible. So another kind of model is called molecular orbital theory. We'll call them MOs for short. Now, there are some similarities between molecular orbital theory and valence bond theory, but there are also some differences. So here's essentially the idea. The idea is that you have, instead of thinking of just the central atom, we're now going to think about two atoms that are forming a bond with each other. Okay, in fact, they may form more than one bond. They may form two bonds or three bonds, right? So imagine, for example, two hydrogen atoms. So these are each hydrogen atoms, right? So the little dot in the center is the nucleus. The circles are the 1s orbitals, right? Remember, hydrogen only has one electron, so that electron in the ground state is in the 1s orbital. Those are called atomic orbitals, right? These are AOs. Atomic orbitals are your 1s, 2s, 2p, 3s, 3p, 4s, 3d, so forth and so on. Now, what we're going to claim with molecular orbitals is that essentially because these are waves, they can interact with each other and they can undergo two mathematical operations. One is essentially addition. The waves can add. So we'll call this addition. Okay. And when they add, what happens is those waves essentially form a new type of orbital where there's a lot of electron density. So the electrons have a high probability of being between the two nuclei, right? So those two waves are adding. In fact, sometimes we even just do it like this. We say they're adding to each other, those orbitals. So we would say that this is a hydrogen 1s. And since there are two hydrogens, we'll put A, meaning this is atom A. And then there's a hydrogen 1s, and we'll call that B, atom B, right? Just so that we know which hydrogen we're talking about. So those two atomic orbitals mix, and they form what's called a molecular orbital, okay? When they add, we call that a bond. Okay, so when the atomic orbitals add to give us a molecular orbital, we call that a bond. And the orbital itself is called a bonding orbital. Okay, so in a sense, it makes sense. I mean, maybe it makes sense. You essentially are adding these two orbitals, they mix, and they do it in such a way that the electrons are now in between the nuclei. So what's the effect of that? If they're in between the nuclei, they're going to act kind of like a glue, right? Like a magnet, like an electromagnetic glue, and primarily electric. they're going to hold those two nuclei together, right? So now you have a lot of density here in between, a lot of negative charge in between, right? Now there's some negative on the outside, right? So some of the electron probability is out here too, and some of it's out here, but most of it is in between the nuclei. And that's just a mathematical operation. You add these two atomic orbitals together, you get this new molecular orbital. When the molecular orbital has the electron density in between the nuclei. So see how that electron density is in between the nuclei like that? We call this a sigma bond. And the symbol for sigma in this case is a lowercase sigma, which is just Greek for S. All right, so there's your sigma bond. So the sigma bond is what you get when the electron density is directly between the two nuclei. But guess what? What we observe in nature is that when waves add, they can also subtract. And this is called destructive interference. So we'll call this subtraction. And you get an interesting result. Here's the two nuclei. Essentially what you get is you do have some electron density between the nuclei, but you have most of the electron density is away from the nuclei on the opposite side. It's almost like they're repelling each other, right? And in fact, this is what's called a nodal plane or a node, and it has 0 amplitude. There's no wave right there. Okay, so it's like a barrier, a no man's land, right? There's no electron density right there. So because this electron density is primarily away from the nuclei, not only is it not a bond really, it's not a bonding orbital, it's really what we call an antibonding orbital. It's actually higher in energy than the atomic orbitals themselves. So this is what we call an antibonding orbital. Okay, the symbol, again, if you look at where this orbital is, and keep in mind it has two nodes. I mean, it has two lobes, just like a p orbital does, right? Or a d has 4. This particular orbital has two lobes. So there's one and there's the other. It's in the same direction. It's in the plane of the nuclei. So the nuclei, you can make a line right through them. So it's still called a sigma, but it's an antibonding orbital. So we put a symbol there. It is a sigma because you can draw a line through the orbital and through the nuclei. So see how I can draw a line through the orbital and through the nuclei? One straight line goes through it. It's actually, it's 3-dimensional, so it's a plane. But to call it to indicate that it's an antibonding orbital, we put a star, an asterisk actually is usually what people do. Asterisk is just a star, right? So you put that up there to indicate that it's anti-bonding orbital. And so let me show you the energetics of this. This is called a energy level diagram. We've talked about it before. So, but this is done a little bit differently because now we have two atoms, not just one. So I'm going to write here HA, so that's our first atom, and then HB, that's our second atom. And remember, there's only one orbital that we're talking about, the 1s orbital, right? So each hydrogen atom has a 1s orbital. So I'm going to write it like this. And, let's call it B and A, right? And each atom has one electron, right? Hydrogen only has one valence. It actually only has one electron and one valence electron, right? So here we go. So here's what happens. The addition part, it turns out, lowers the energy of the atoms relative to the separate atoms. So these are two separate atoms, right? Those are separated. They're not bonded. So when you have two hydrogen atoms that are not bonded, you have 1s1, 1s1. They're not bonded. But now, when those two orbitals get near each other, when the electrons get near each other, they mix together. So in a way, it's a little bit hybridization. These orbitals are mixing. But now, what's the big difference? The orbitals that are mixing are not from the same atom. Remember, with hybridization, you're mixing the 2s and the 2p's, or the 3s, 3p's, and 3d's. Those are all in the same atom. Now we're talking about mixing of orbitals from different atoms. And that's the power. That's one of the most amazing things about molecular orbital theory. And that's why it's actually in many ways more accurate than valence bond theory, is that now it's talking about, no, it's not that one atom is an active participant, the other one's just sort of there. They're both of them have waves, and these waves are mixing together from the separate atoms. So there's a lot of predictive ability with molecular orbitals. So here's what you get. Here's the energy level diagram. The new orbitals, here's your sigma 1s, right? So remember, there is no sigma A or sigma B because this is a new orbital that's a mixture of both orbitals, the 1sa and the 1sb. So this one right here is the molecular orbital. So this is an atomic orbital. This is an atomic orbital, just like we learned in chapter 6, and we did a little bit, we also did it in chapter 8. But in chapter 9, now that we get to this is your molecular orbital, and that's the addition. The addition is lower in energy than the atomic orbitals, which means if the electrons are in that orbital, this molecular orbital, you got a bond. And now these atoms are attached to each other. But what about the sigma star? It turns out it's got to be just as much above the energy of the atomic orbitals as the molecular, as the sigma 1s is below. Conservation of energy, essentially. In other words, if you were to measure the difference in energy between these two orbitals here, from here to here, this one's up the same amount, right? So we just draw little dashes like that, right? So here's your sigma 1s star. Isn't that interesting? Okay, so now here's what happens. Offbow principle. Remember, electrons are negatively charged, nuclei is positive. So what do electrons want to do? They want to pile into the nucleus. They're attracted to it. But there's a limit. They can't get all the way into the nucleus because of the Pauli exclusion principle that keeps them sort of, a limit. You can only have two that are close to the nucleus, and then the other one's got to be further away, right? So what these electrons do is they pile in. But they pile in according to the Pauli exclusion principle. So you can only have two down here, right? So these two down here are the same as these. I haven't created two new electrons. It's not like there's four now. These two went down to there. There you got your sigma bond, right? This orbital this is a bonding orbital. It's not an atomic orbital. It's not an orbital for one atom. It's a bonding orbital. So now this orbital, which we drew right here, those electrons are in there. One spin up, one spin down. So there's a little bit of energy for one to flip its spin, but you gain so much energy by coming down all the way downhill, okay? Now, can you test it? You can definitely test it. You can do all kinds of experiments. What you can do is you can measure like the energy difference between 1s and 2s, put a photon in and get it up to there. But now you can do this. You can put a photon in here and measure the difference between these two. You can promote one of these electrons up to there and measure what the energy is. And it turns out that orbital exists, right? If that orbital wasn't there, if it didn't exist, you would shine your photon in and it just would go right through the atom. Remember that energy matching idea that Bohr came up with. So that means there's got to be an orbital up here, and we can measure its energy difference and actually show, oh yeah, this energy difference is, halfway up between here. This distance here is twice what this distance here and this distance here is. Okay, so that's the idea of molecular orbitals, right? And you have this idea of a sigma bond. So I'm going to show you one more thing, and then we'll work on problems tomorrow. This is sort of the theory background. The next thing is the idea of what's called a pi bond. And we use the symbol pi, okay? The Greek letter pi. So remember, here's the idea. If you have a orbital, so let me draw it this way. If you have a molecular orbital, so sigma and pi refers to molecular orbitals, not to atomic orbitals, right? Because atomic orbitals are for the individual atoms. Sigma pi refers to bonds. So if you have a sigma bond, what I said was that you can draw a line between the nuclei, a straight line that also goes through the orbital, right? So here's your sigma bond. Okay, now that also works for a sigma star bond, right? Because your sigma star bond looks like this. So you can still draw a line. Okay, there's no nucleus there. There's your node, right? You can still draw a line that goes through the orbital and through the nuclei. But since the electron density is away from the nuclei, right, on the opposite sides, it's like being pushed away almost. That's called a sigma star bond. Okay, antibonding. Antibonding orbital. Bonding orbital. So here's what's interesting. It turns out p orbitals behave more interestingly. They have a couple of possibilities. So here's the idea of p orbitals. How did we get these? We got these from s orbitals, right? These came from s orbitals. We mixed the s orbitals to get the sigma orbital. In fact, sigma means s, right? So that's why they use that nomenclature. So same thing, p, what's the Greek letter for p? Pi. So we call it a pi. Molecular is pi. So the molecular orbitals use Greek letters, and the atomic orbitals use, I guess, English letters, right? So here we go. So here's what happens with the p. If you have a p orbital, so here's the nucleus of one atom, and let's say this p orbital is directed like this, right? Remember, that could be a p orbital. So here's your p. So we'll call it a 2p. We'll use 2p, second shell. We'll call that A. Now let's take another atom. Okay, I didn't draw it the same size. I meant to draw this the same size. So here's another 2p orbital, but this is for atom B, right? So this could be like carbon and carbon, for example. 2 carbon atoms are bonding, okay? Now, here's what happens. Same idea. You get this. You get high density of electrons right there, and then you get some density out here, okay? Now, that's called a pi 2p. This is the addition. Okay? Right? So this is where you're adding them. You get that. See how there's a lot of electron density in there? That's a bonding orbital. There, it's holding the nuclei together, right? There's also some on the outside, but don't worry about that. Now, you can also get subtraction, just like we talked about. Okay? So here's what happens when that occurs. Again, you get, oops, sorry. You get you essentially get the same thing that we got with the sigma. You get a lot of density out here, but you get a node. When you see a node, that kind of tells you, oh, it's an antibonding orbital usually. So this is called pi 2p star. I'm sorry. I am so sorry. I used the wrong symbol. This is sigma 2p. This is sigma star 2p. Now, why did I call it sigma? Because you can draw a line or a plane through the nuclei and through the orbital, right? That's how we defined it. Here's your nuclei. You can draw a line right through the orbital and through the 2 nuclei. Okay, that's cool. But now here's what happens. So that's a sigma bond. The sigma bond lies in the same plane as the nuclei. Now imagine you take your first atom and the 2p orbital is like this. So again, imagine this is a carbon atom. This is another carbon atom. There's your 2p orbitals. 2p, right? So this is 2p from atom A, and this is 2p from atom B. They're going to mix. And they mix in a very interesting way. Here's what you get. When you do addition, you get this. They add together. These lobes up here add together, and these lobes down here add together. And you get, looks like a sandwich, a hot dog. So look at this shape. It's different, right? But this is electron density between the two nuclei, right? So is this. And you have some above the nuclei and some below the nuclei. So there's actually two regions right there. Okay? So here's what we're going to call this. We're going to call this a pi 2p. And the reason that we call it a pi is that you cannot draw a line through the nuclei and through the orbital. The orbital's up here. See, you'd have to draw different lines. If you have to draw more than one line to get through the orbital and through the nuclei, then it's a pi. So we call that pi. Okay? Now, what about antibonding? So there's your bonding orbital. See how there's no asterisk? There's no star? If there's no star, it's a bonding orbital. But what happens if you do the subtraction? You get this. It's kind of hard for me to draw it. So here's your two nuclei. You get a lobe here, a lobe here. Let me draw that nucleus a little closer. A lobe here and a lobe here. And there's nothing in between, right? So this is also pi because you cannot draw a line through the nuclei and through the orbital. The orbitals are above, right? There's 4 lobes. This is a new orbital. It has 4 lobes. So it's pi 2p, but it's an antibonding. You can't draw, I'm sorry, it's pi, so you can't draw the line through it. It's star because it doesn't have any, there's no bonding region, right? All of the electron density is away from the opposite nucleus, right? So these two are adding in 2 different ways. This plus this is giving you this one. This minus this one is giving you this one. So now we have 6 different types of orbitals. We have sigma 2s, right? Or 1s, I'm sorry, I did 1s. We have sigma 2p. We have sigma star 1s, sigma star 2p. So those are the first 4 that we did, right? So we did these 2 here, with the S ones we did earlier. But now we have these pi's. So we have pi 2p and we have pi star 2p. So you now have 6 possible molecular orbitals. And so what we're going to do on tomorrow is we're going to start doing we'll do the Alex problems, but I want to show you how these orbitals, where their energies are, and how to fill out these diagrams that we'll talk about. They're called molecular orbital diagrams. It's very interesting. So essentially, we've got really, in a way, depending on how you think about it, we've got 2 types of bonds. We've got the sigma, where you can draw a line through the nuclei and the orbital. And then we have a pi, where the orbital sits above the line that goes through the nuclei and below, above and below. Okay, that's called a pi. And then you got the stars. So the stars are the electron densities away from the nuclei. So it's antibonding. And then you got the ones without the star, the bonding orbitals, where you have the electron density between the nuclei and that holds them together. So unlike any other bonding theory now, we have a theory that actually has orbitals that are anti, right? They actually don't result in bonding, but the opposite. They result in sort of, pushing the atoms away from each other. So we'll talk about the ramifications of that on Thursday, and we'll go through some of the Alex problems. So take care.